Hello, everybody. Welcome on this Friday for our ABEI4 seminar. And today we have Ankita Raturi from Purdue, along with Avni, also presenting on Ag Informatics. And Ankita is an assistant professor at Purdue, and she's an import into agriculture, as far as I can tell. She has her PhD and master's both in computer science related disciplines, specifically in informatics, and then she was working with Steve Mirsky and others in the DC area before she joined Purdue. So I'm really looking forward to hearing her take on informatics, um, and I think we'll have questions on the side. If you want, you can address them, or we can wait until the end.
Okay, yeah, that sounds good. If there's something that you think is timely, feel free to just let me know there's something in the chat I should look at.
Yeah.
All
Okay.
right, cool. And if I may share my screen,
Yep.
you should be able to see my slides. Is that correct?
That is correct. That's wonderful.
Fantastic. All
All right.
right. Well, thank you so much for having me. I'm really excited to speak with you all and share with you some of the work that I've been doing in agricultural informatics. So as Girish mentioned, I did come from a computer science / software engineering / informatics background, and then had, but even then my work was looking at agricultural challenges. And so some of the work that I'll share with you actually started back in grad school. And then after that, when I was at USDA, I started some of the cover crops work. And so a lot of the work that I'll be sharing today started before I actually even joined the faculty here, which I did in 2019 fall. So this makes a year. So I'll be describing generally my approach and some of the projects that I've been doing in agricultural informatics, specifically around design modeling and software engineering, and really focused around resilience in agriculture. So food is obviously essential, but I think the thing that always occurs to me is that its infrastructure is fairly complex. And you'll notice that there's a desire to manage this agricultural complexity at scale and transition to more sustainable ag practices. And this has inevitably brought us to consider, the range of technologies that we can design to overcome a range of challenges in agriculture. So when we think about this, it includes things like, if you want to handle in-field spatial variability, we might think about integrating sensors across scales, whether it's sort of in-field sensors all the way through to remotely sensed data. If we want to do things like identify pests and weeds, we might look to machine learning algorithms to do some of that type of work, all the way through to thinking about ways in which we might want to be able to integrate research and practice. And I'll share with you actually some of the work that we've been doing on decision support tools later in this talk. And so I always like to share the acknowledgement that we have been designing tech for agriculture for a really long time, right? Tech is old in that sense, whether it was the plow, whether it was GMO, whether it's the tractor. We've been designing tech for a really long time, but it's the ingredients and the things available to us that have changed. And so now we have bits and bytes that we can play around with. And so we're experiencing this fourth industrial revolution in agriculture, right? The digital ag revolution. So we went from having purely analog farms to a situation where, farmers and consumers and everyone else between are being faced with this glut of data. And so the challenge in the sort of coming century will be to try to think about how we can harness the power of digital technologies to enable us to gain insights to both improve our systems, but also sustain and grow with care. And so in my talk today, I'm going to describe to you work at this intersection or this boundary, which is where most of my stuff happens as we begin to design ubiquitous digital tech for sustainable agriculture. So I think it's important to also then tease apart technology, again, as a way to frame some of the things that I'm going to be describing to you today. So you can think of it as hardware and software, whether it's in cyber physical systems or just technology in general. And hardware really is focused around manipulating the world, right? You're trying to manipulate reality. You have a tractor that's actually dealing with these physical interactions. Software, on the other hand, I find interesting because it allows us to manipulate information or models of reality, right? To make your tractor a smart tractor, you basically give it a model of the real world. And then first you manipulate that model before then it manipulates the earth. And so it allows you to start to engage in these like hypothetical interactions and sort of hallucinate about ways in which you can change the world before you actually move something, right? So software enables us to create these abstracted, grounded models of these real world systems and engage in some really, I think, cool things like predictive analytics and do some interesting problem diagnosis to coordinate like we are today across time and space. but also then do some things that are a little bit more actionable, like allow for people to provide decision support and do some systems level analysis. And so I wanted to at least describe some of this as the problem that we're facing today. I also tend to bucket the challenges that we're facing in the design of technology for agriculture in these 5 different areas. So there are these essential challenges, in my opinion, that we encounter as we're building tech for ag. And the first one really is, are we building things that are useful for actual users, right? And I know this sounds a little tongue in cheek, but I think it's important that when we're trying to design technologies, that we're actually doing it because somebody has a problem in the world that we're actually trying to address, or that we're doing it in concert with domain experts. And I say this as somebody who's coming from the tech side, because oftentimes we'll design a hammer and then go looking for a problem. Whereas I like to argue that we do take this community-driven approach, and you'll see that in my projects, so that where we're actually building things that have utility for specific users. Similarly, it's important for us to consider usability. So how intuitive are the user experiences we create? Why aren't our technologies as intuitive as some of the ones that are designed for the consumer, like the iPhone? And so these are some of the things that at least I consider in the design of tech. Interoperability is a big challenge. I won't talk about it too much because I think we hear about it a lot. But really it boils down to this idea of can we move data across tools, devices, and systems? Can they talk to each other? And can we actually then move beyond having these like siloed data sets and siloed tools? The fourth issue is one that has been gaining a lot of traction recently, or at least over the last few years. And it's really thinking about trust. And the question boils down to asking, do our users trust us in the process of designing technology? And do they trust us with their data? And I think this is something that is fairly accessible to most of us, because when we think about even the technologies that we use, whether it's social media or even Zoom, we ask ourselves a question of whether or not we trust these tools with both our data and with our data. And so the last one that is important for us to consider is then thinking about resilience. Not just are we building tools to support resilience in agriculture, but then reflecting back, are the tools that we're building robust, reliable, and adaptable, right? We don't want to just move fast and break things. We actually want to build things that are here to last and that will change as our agricultural systems change. And I think that's an important thing to consider as a designer of technology. So with these things in mind, my lab really focuses around this core principle that software gives us the ability to manage agricultural complexity across scales. And you can see this sort of play out in a couple of different ways. So some examples are listed here. You can think about it as, can we design software to help trace inefficiencies with data and resource flows through a particular system? And I'll share some about that a little later. Can we use software to check for compliance through automated model checking, right? So these are traditional CS methods like model checking that could be used actually to help benefit our analysis and our assessment of agricultural systems. Or can we just identify obfuscated bugs on farms, whether it's a software bug, which is basically a bottleneck, or an actual bug, like some of my colleagues in weed and pest science do. And so there are a bunch of different ways in which we can approach this problem. There are 2 core principles that underpin my work. And so these, I think, are things that if we all agree on, then everything else in the presentation will be totally in concert. But if we don't, then we might have some fun questions later on. The first principle is that farms are complex adaptive systems. And that is, they're spatially and temporally complex. There's a lot of heterogeneity in both the systems themselves, whether it's a production ag system in the Midwest or a diversified farm out in California. It's sort of, you see heterogeneity across scales. The second part is that everybody models, whether you're collecting data for your crop layout, or whether you're making a spreadsheet describing certain kinds of attributes about your planting plans, or if you're using a piece of remotely sensed imagery. All of these are different information artifacts. And so in that sense, as you go through this process of data collection, of representing data about our farms, you're modeling. And so it's with this theoretical framing that I approach the work that I'm describing to you today. I usually just like to share the slide in case you're curious to go and think a little bit more about all of the software disciplines that I draw from. I think it's oftentimes we treat computer science as a little bit of silo, but there are a lot of different little things going on. So, you can think about it this way, that if you're designing a remotely sensed algorithm, a remote sensing algorithm, then you might look to computer science to draw for reference material. But if you're trying to think about the user experience of somebody interacting with technology, then you might look to the fields of computer-supported collaborative work, which is where things like Google Docs come from, or human-computer interaction, which is where we consider things like user interface design and user experience design. But it all sort of boils down to the cyclical approach of product design or development, product design and development, or software engineering, right? So you start by understanding user requirements, you then design the user experience, we then do some work trying to develop the software and information architecture, and finally we implement a product, test it, and refine it. And so the rest of this talk, I'm going to describe to you a couple of different projects using this framing of design, modeling, and software engineering, and some of the communities of practice that I work with. So just if I zoom out a little bit, I wanted to share, and this is a lot of information, but fortunately this is recorded, so you can come back and read it later at your own time, a sort of a bird's eye view of what I see as the challenge areas within each of these pieces. So in human-centered design, you know, actually understanding user needs is a big issue. A lot of my work really focuses around this, and I tend to take a qualitative research approach to first understanding and articulating user requirements. There's a lot of work around data privacy and agency, and all the way through to these far-reaching issues that we're beginning to grapple with, like what is the future of work in agriculture as we begin to engage in a lot more digital work. The second area is modeling. And again, there are a couple of different challenge areas. My work is really focused on these first two, and some of my far-reaching goals are to actually start to think about moving from technology as something that we just use to actually thinking about technology as a collaborator. So moving from descriptive to predictive and prescriptive analytics for agricultural systems design. And so there's a little bit of information about some of the early projects and some of the directions in which I'm going. Similarly, when we think about software engineering, a lot of my work right now is really around decision support tools, and then some of this environmental assessment work that I'll share with you today. But if we sort of look downstream, really, we want to move from decision support to actually being able to design recommender systems, simulation and complexity management tools for agriculture, right? So why just stop at decision support, but actually try to think about how we can move towards having intelligent assistance. Okay, so that's a lot of it of framing. Today I'll share with you now two specific projects so that you can dive a little bit deeper into some of the work that I've been doing. The first project will be around environmental assessment, focused around small farms in California. And then I'll zoom out to the other end and we'll look at some decision support tools. I'll share with you one of the decision support tools that we're building, primarily geared towards production agriculture, to help people with cover cropping in the Northeastern United States. Okay, so this work was really something that I started in grad school and still continues today. And the way in which I came to it was realizing that, you know, there is this growing demand for food that is grown sustainably, raised humanely. And so consumer interests in the provenance of food and farmer interests in transitioning to more sustainable ag practices have led to this host of environmental assessments being conducted of farms. There's also this rich policy and regulation context that requires or encourages people to conduct a variety of environmental assessments. And so the core question then becomes, at least from my perspective, how do medium to small scale sustainability oriented farmers model their agricultural systems when they're assessing their environmental performance? And I should caveat this by saying, when I say model their experience, remember again, when I say everybody models, right? So it's not just, you know, creating a machine learning algorithm to predict what's going to happen next, but it's also thinking about how they're actually representing different kinds of data about their farms in order to do things like track resource flows or monitor effects of different kinds of cultivation practices and so on. And so what I did from here was I said, let's go visit some farms. And so I did a qualitative study with about 16 farms throughout California, sort of starting with farms that were about an hour south of San Diego up through to several hours north of San Francisco. So a pretty broad geography. And so they covered a range of commodities and environmental assessments and ages and environmental values, sort of mostly to try to acknowledge this idea that sustainability is not binary and that farms are fairly diverse. And so given this, what we ended up with was a pretty heterogeneous set of farm data that allowed for us to then start to think about what are some of the commonalities in their models. So at each of these farms, I conducted interviews to start with, some surveys, and collected information artifacts. And these included things like spreadsheets and screenshots of software and farm layout diagrams and other clues to the information management process that was going on at the farm, right? So my goal was really to try to be able to explore information management practices throughout the spectrum of sustainable ag, which requires a pretty diverse set of systems. And so we found a couple of commonalities, right? So a lot of small scale farmers were collecting data through these three primary ways. The first one was through observation, which I think a lot of these are actually true regardless of what type of farm you're going through. These are the primary ways in which people had been collecting data, at least in 2016. And so there's a lot of observation, which I think still continues, a lot of sampling, of different parts of their system, and then a lot of analysis of each of these samples. And the third one, which in 2016, I think there was interest in sensing technologies, but the proliferation of low-cost sensors hadn't really kicked off yet. And so there was some in-ground sensors, but not a lot of equipment-mounted or remotely sensed imagery used in this type of farm in that time and context. And so I want to just make sure that I give you that caveat before I share with you the rest of the results. So what did this data look like, right? We saw a lot of environmental data, and this was predominantly coming from outside. So folks would have weather data, there was land data, they would record their observations of weeds and other pests. There was a lot of operational data, which was primarily financial and labor and a lot of things about logistics within the farm. And then, and I know I'm going up and down, that's because I want to focus then on the second one actually, which is resource data. So when we were thinking about environmental assessments, most of those required the tracking of resource data and the actual reporting of a lot of water and energy and inputs to be able to actually then give you some sort of sense of what was going on the farm. And so I'll share with you some of the artifacts that we found, right? So if you start, you'll start to see things like a whole range of information artifacts, in this case, just for resource tracking, right? So they're all different, they take different forms, they all look different, they're formatted differently. But if you drill down to what is the actual data captured in each of these, what you end up with is you find that each of the farms are tracking the rate, the date, what it was, and why it was done, right? So from this really varied and seemingly unconnected set of artifacts, what you end up with is something that you can actually create a data model around, right? I now know what each of these folks need to be able to track when they're engaged in resource tracking. So similarly, we found three genres of models the people were using. The first were models that represented space. Here, what we found was that different goals led to different levels of formality. So you'll notice the first one in the top left, which is the vineyard layout, is fairly informal, right? It was a hand-drawn diagram. And it was initially created for them to be able to show to visitors who are coming out for a wine tasting. And what they quickly realized was they actually didn't have a good map for people to actually be able to coordinate work on the farm. And so they opportunistically used this map to be able to coordinate activities among workers, being able to say, okay, here you go, apply these inputs there, you need to go prune these trees. And this seemingly innocuous artifact became this very rich document that people were using to engage in collaboration on the farm. On the other end of the spectrum, we also found things like these farm satellite maps, but sometimes they were just a little too complicated. And so it meant that people didn't actually end up using it for anything particularly meaningful in this particular case. So they had these cool maps, but they didn't have a clear task to attach them. And so they were mostly left unused. And so we see a lot of these different types of things going on at farms where a lot of different maps were used for different kinds of reasons, but they were all at the end of the day capturing whatever the person needed to change the most, right? So if you look at the bottom two, you'll notice on the orchard, they only really showed what was planted in each of those fields and then the infrastructure, and then everything else that was changing really rapidly went into spreadsheets. Or I should have said, they were really capturing what wasn't changing the most. Similarly, in the greenhouse mousetraps map that you see on the bottom right, you'll notice that they didn't actually tell you what microgreens were planted in each of the beds because the turnover there was like every 2 weeks. And so what they really had marked there was just like the mousetraps. And so it tells you something about what people are prioritizing from a representational perspective, what they actually think needs to be represented in a specific type of map. We also found a lot of map models that represented time. So every farm had a farm calendar. And what was changing at different ones was what type of data they were collecting in each. I think the one on the left is particularly interesting because this was actually used to track resource use and labor during, in this example, the pruning season. And so that tiny little card actually has a lot of information about what inputs were applied, who was doing what, how long it took to do different things. And then these were actually put together into a folder for the farmer to be able to then reflect later on how efficient their different activities were. Finally, we saw a lot of combined spatiotemporal representations of farms. A really popular one in small farms is a crop layout. And so oftentimes you'll see something like what's on the left, which is a layout of the entire farm and an annotation of what's being grown where each time the crops are rotated. And so what you end up with, especially this was something that we saw at this farm, was a thick binder that consisted of maps on maps. Every time something was rotated, they would update those maps, and they were just literally redrawing this. And this is fairly common even today. Even though we have tools like Farm OS and Tend and a lot of tools that are geared toward farm management and small farms, the crop layout diagram and this model of working is still fairly common. This is oftentimes paired with a spreadsheet that looks like the one on the right, which is a single field. And what this literally says is, this is the field and here are what's being planted in each of the beds. And then there's some annotation. And so this one I think is kind of fun, right? Because it's a digital artifact. It's a spreadsheet that they printed out, but it's still being annotated and it never goes back. And so what it means is you end up losing a lot of opportunities to engage in analytics about what's going on in the farm, right? So one of the things that a lot of the folks that I would speak to is that they would describe things like, well, if I had all of my maps digitized somehow, I would be able to get support about what I should be planting in that particular bed next time, right? So maybe I don't want to plant a legume after a legume if I'm trying to do a particular kind of crop rotation with soil health goals in mind. And so these seemingly innocuous and unrelated artifacts can be connected, and I think should be connected in order to allow us to start to design more interesting tools for farmers. And so there are a lot of implications for design. I won't go through this full list, but I leave them here to at least help you get a sense of why we then pivoted to designing a modeling framework to try and start to knit together each of these different kinds of data. So if we sort of look at the range of data that we've looked at so far, you'll notice that each of these are collected at a specific place and time. They all have a specific spatial scope and a specific temporal scope. And each of these data represent attributes of the system that allow us to meet a particular modeling goal. So then the question for at least us at the time was, before we go ahead and start building tools downstream, whether it's decision support tools or farm management tools, how do we knit all these data together? And so the approach that we took was to then design a modeling framework that actually starts to layer on some of these data. So we took those qualitative data that we collected during the interviews and coded them in order to be able to identify information artifacts or to identify specific types of data that we might want to actually then put together. So we went from those qualitative findings to an information model. Just a moment, please. I'm going to hand over the baby. Sunny, maybe trade. All right. Cool. So going from these qualitative research findings to information models, I think is where I left off. And so before we actually went ahead and designed a formal modeling language, we also did some informal model checking. And so we made this little board game that we took out to farms and took out to farming conferences and asked farmers to try and model their farms using each of those Lego blocks, right? So we can start to now think about how do they layer on different kinds of data. And what we ended up with was the MOS framework. And this is something that I can now actually code up and I can have different kinds of tools use, right? So there's an abstract model, there are these domain specific elements, and then there are a couple of different ways in which we can subset that model. So the abstract model really consists of, components that allow for us to represent the system as a whole, different components, different activities, different resources, and then data associated with each of those. And the domain specific elements allow for us to instantiate these abstract components into something that becomes meaningful for example, an actual environmental assessment tool. And so you can see the architectural diagram or the less formal version of that here, where this is just the abstract model itself. And so I won't walk you through the entire modeling language. That might take a while. So instead, I'll just give you a quick scenario so you can get a quick feel for how this works in action. So if you consider this orchard, here you have trees planted in grids and you have a cover crop planted in the middle, right? And so if you want to, for example, engage in some sort of cover crop subsidy program, let's say there was one in California, then what you might want to be able to do is report, what the cover crop was, how the biomass was, and some other attributes about it itself. And so what you really want is a model that actually allows for you to lay out your entire field and then associate data with it. So you can then use those building blocks to be able to start to create a system model that represents, the field itself, different layers of trees and crops, and then start to attach data to it. And so this is in effect something that would be under the hood when we design an environmental assessment tool that goes on top of that, which is sort of roughly the direction that we're going to go in next with some of this work. Similarly, if you have a variety of data about, for example, different kinds of issues that you're seeing in a farm, the power of being able to bring these different data together is really apparent when you do something like this, right? So if you notice here, you might maybe sort of tap information or tag data for specific trees or sample productivity in different places. And it's only when you have them clustered that you're able and layered that you're able to say, hey, actually, maybe there's something I need to go investigate over here. There's a lot going on. Maybe there's a citrus greening issue, as opposed to, just having isolated incidents that you can't connect. And so it's really when you start to actually layer symptom data that you can begin to contextualize seemingly unrelated issues. And so that's a big part of why we went the modeling language route for this first piece of work. Right, at the end of the day, the MOS framework is meant to offer a means to capture all that heterogeneous farm data into a single, coherent, changeable system model. And it's based on that we can then build these different tools for farm level information management, for decision support, for environmental assessment. And so this essentially forms the underlying information architecture on top of which we can build farm level modeling tools. And so from here, we're doing a lot of refinement now, especially as I start to sort of dip into other domains. So the cover crops work that I've been doing, we have a lot of interest now in refining MOS to have components that represent cover crop data specifically. I'm branching out into some more general agricultural ontologies work. So there's a group that I work with called Open Team, where we have a bunch of different folks who are developing a variety of open source farmer-facing tools. And so I'm putting together a common ontology for each of those tech teams to be able to use in their design of APIs and the tools themselves. And then my lab is also producing an API focused around plant data. Specifically, there's a plant data service, which I won't share with you today, but you can ask me if you want to chat more about specifically plant data APIs. And then I'm also doing some work beginning to try to explore some of the tools that I talked about. So trying to find partners for each of those different tools so we can actually start to build things using this coherent information architecture under the hood. Some of this work went a little bit on hold because this year, I don't know if you heard, there was a pandemic. So in about March, earlier this year when the pandemic hit, I pivoted some of this work and started another project focused around the design of community food coordination tools. And this very much builds on the lessons that I've just shared with you so far, especially as we're trying to look at connecting producers and processors, buyers and consumers in these uncertain times, right? And so we did a lot of qualitative research earlier this year, and we're now just beginning to do the software analysis and identifying specific projects that we want to turn into design projects. And so if you'd like to get involved or learn more about this specific type of work focused around smaller farms, feel free to check out the URL at the bottom. That's resilientfood.org. And I'll be updating that again. So the project is currently, we're applying for funding right now, but if you want to find out more, we'll be regrouping basically at the end of the year. So that's a lot about the smaller scale end of things. And I want to turn my attention to the production ag side of things. Here I'll share with you some of the work that I've been doing to support cover cropping. As Girish mentioned, this is stuff that I was doing when I was a postdoc and has continued since. And my lab has sort of grown to really look at focusing on decision support tools, especially since we see there's such an interest and a lot of desire for tools that are built both beautifully but usefully. And so I'll share with you a little bit about how we have gone about that. I'm just going to do a quick time check. So I I think I have half an hour remaining. Is that correct, Gish?
Yep, yep, we're doing great.
All right, all right. So cover crops, I think I might be preaching to the choir. I suspect most people already know what cover crops are, but for the other computer scientists in the room, I will give you this tiny primer that I was very excited to receive a long time ago. And it's this idea that cover crops are plants that provide ecological services. And these can include things like nutrient cycling and improved water quality. They can help improve soil organic matter. But at the end of the day, a cover crop is only as effective as it is in a specific place. And so there's this cognitive burden as people are trying to balance crop genetics and environmental conditions and cultural practices and system management to be able to identify the right cover crop for a specific time and place. And so cover cropping is this very site-specific venture in which you actually need to know a lot about this particular place and what the conditions are before you can decide what cover crop you want to plant. And so in that sense, effective cover cropping is fairly knowledge intensive. And so what we found was there are a lot of different tools, a lot of different data sets. There's a lot of rich information, right? Because a lot of really awesome folks have been looking at the efficacy of cover crops and doing a lot of research in this space for a very long time. And so it means that there are a plethora of tools also that have come out to help people do different things like select species and collect and calculate seeding weights and make mixes. There's a lot of supplementary data on top of that, where people are using a variety of different maps and weather data and soils data to then be able to try and figure out at the end of the day, what cover crop should I be using and how should I manage it? The issue at the end of the day is that this sort of plethora of data, this glut of data, results in data that is not necessarily site specific. It's pretty hard to use. Some of it's proprietary, and you have a lot of these different silos, whether it's with tools and data. And so people are having to hop from place to place to be able to then identify what they need to do from there. I think this was a comment made to me once in a discussion, and Chris said that I shouldn't bother corn farmers with potato questions. And I love this, right? It, for me, was like the epitome of what decision support is about, right? You want to provide timely and specific guidance, right? That's what I really want to do. Because there's all this data and I could throw it all at the user, but if you're interested in one specific type of information, then I should drill down for you. Right? That's the whole point of technology, right? It should offer that automation support. And so in order to be able to help with that clever drilling down, I look to people who know cover crops better than I do, and I work deeply with communities of practice. So you'll notice with each of my projects, I do not take the role of the agronomist or the agriculturist. I have to work with domain experts in order to do my job right. And so this work was something that was driven heavily by the folks at ARS, at NRCS, at SARE, and in particular was really made possible by the work done by the Northeast Cover Crops Council. And so these are our partners for this project and our community of practice for these specific tools. So as we started to dig in, we identified 3 user groups for the cover crop tools that we're interested in making. There were growers themselves, where we wanted to help them be able to meet their farming goals. We were also interested, and this is something that wouldn't have occurred to me if I was working on my own, but they're advisors, right? A lot of the folks who are cover crop experts talked about this idea that a lot of growers are actually getting advice from other people on cover cropping, for doing things, including selection and management. And so it's just as important to ensure that our decision support tools can help support their advisors in addition to the growers themselves. And I like the third group because I feel like I fall into that bucket, which is people who are explorers and just trying to learn more about cover crops. But that's also a group that really covers novice farmers or people who are novice cover croppers who are just trying to learn a little bit about what's going on in that space. At the end of the day, you'll hear a lot of people talk about, I want, full stack decision making. I want every single decision supported. And so what we'll see a lot of different tools. But the reality is each of these tools are disconnected, and there is no such thing as full stack decision making because everyone's path through that decision making process is different. Not everybody needs all 8 of these. Some people might just want support with the economics or just support with doing the seeding weight. And so it's important for us to, in effect, create this choose your own adventure user experience for different types of farmers and advisors. So for the rest of this talk, I'm going to focus on the species selector tool. We're actually working on the first 4 tools, and we have plans down the line for this full range. And so this is a lot of the work that I've been doing in collaboration with Stephen Mirsky and Chris Reber-Horton at NC State and ARS. And I think I have a link to the website for a lot of this work later on. It's precisionsustainableag.org. So let me describe to you a little bit about the architecture and the design of the tool itself. So we have this modular architecture for the tools that is intended to allow for interoperability among them, going back to sort of what I was describing as those critical challenges. We're also trying to support a seamless user experience. So I should be able to enter data once and then engage in these different question asking scenarios or these different decision support scenarios differently. And it should be able to help me build on my previous decisions incrementally. And so we are focused on this first one, but you'll notice the same architecture has been used for each of these, right? So we have data separate from the user interface itself. And what this allows us to do is have the experts drive the data and the user needs drive the tool, right? So expert information tells us what cover crop data should look like, and I'll share that with you in a sec. And then the user requirements or desires or challenges determine what the actual interface looks like. So when we think about what leads to effective decision support, there are these 2 pieces, right? We need high quality regional cover crop performance data, as well as some local field conditions. And this is often stuff that happens behind the scenes. And then on the front end, what you need is an improved user experience that reduces information overload. So we started with a range of existing data and tools. So the Midwestern Cover Crop Council has a fabulous selector tool, which I believe they recently updated, which we took a lot of lessons from their work. And then we also looked at the NRCS seeding rate tool to be able to get a lot of information on how seeding rates work. And then for some of that supplementary data, we also started to pull together pieces from the USDA plants database, from ITIS for plant names, from Web Soil Survey. And actually our colleagues at NC State built us a weather API that we could use so we could also get some local weather information. And so you'll see some of these pieces come together as we move forward. So the data itself was actually kind of fun to knit together in the end. So we had this broad range of data that I just shared with you, and we put them together into these data verification sheets. We then had about 5 teams, or we had 5 teams of about 56 cover crop experts. And so each of those teams were folks who were focused around a specific plant hardiness zone within the northeastern United States. These data verification sheets contained all of the cover crops, so about 64 of them. And for each of those cover crops, we had about 117 variables. Some of these numbers have changed as we've been going through the process, but that's sort of ballpark numbers for you to keep in your mind. And then we had 9 categories of data, right? So basic agronomics, environmental tolerances, soil conditions, and so on and so forth. And so each of the teams met about every 2 weeks. We had 2 postdocs running these data verification calls. To then be able to actually either bring in the data where it didn't exist, or refine it or verify it where they needed to. So if you look at the data itself, we have this data dictionary that shows you at least some of the variables, just so you can get a sense of what it looked like. And it ranged from all of those different categories, but it included things like, how you can seed it, what the cost of those seeds are, how it was going to behave in different areas. And you'll see some of the data sources as well in here. We also had variables around what the actual ecological services were that each of these cover crops were good for. And so this was a lot of work on the data experts' part, because they were actually rating each of the cover crops with their ability to perform each of these different services. We had a lot of data around environmental tolerances. So for each of those cover crops, you'll notice that there is some information about what that plant can tolerate. There's data about planting factors. And so it's a lot of really interesting, rich data that you wouldn't necessarily want someone to have to sift through on their own. And so we're packaging it all up, and you'll see it in use in the tool that I'll share at the end. But this is sort of why we're building this plant data service, right? You want people to be able to query this data set and find exactly what they're interested in. And so we should hopefully have a public API coming in 2021 that will be able to serve up some of this interesting plant data. Okay, so then let's turn our attention to the front end, to the design of the tool itself. And I want to disambiguate between 2 concepts real quick before I move forward. So consider the design of a bridge. Software engineers love to look at bridges as analogs for what we build, although ours are not always so monolith. But consider the design of a bridge. In addition to the structure of the bridge, you also need to consider how people are going to use it to interact with, and that's the user experience. And so oftentimes the user interface is really what you're looking at when you're thinking about design. But when you think about how you want someone to flow through a specific tool, that's really user experience land, right? You need to think about how you want someone to go down a decision-making pathway, which is critical when you're trying to think about design decision support tools. So we focus our attention to the more cover crop tools, so to the more cover crop experience. Sorry, we focused our attention more to the cover crop user experience than the aesthetics alone. So you can see here, there are a range of tools that people use to buy or find information about cover crops. Turns out, yes, you can buy cover crops on Amazon too. The user experience is not the greatest, but it still taught us something about what are the different ways in which people are engaging with cover crop data from a software perspective. And now the dirty truth about all software, which is that yes, it does typically start as a scribble on a piece of paper, but these are actually low fidelity prototypes. And the one in the center was kind of fun, and it actually ended up in our final design. And so you can see that it actually has a toolbar on the side and each of the different cards that you can then swap. And what this allows us to do is very low cost testing around a basic design before we actually go ahead and build it. From there, we then create these high fidelity mockups. And so you can actually see how the tool works from end to end in this particular GIF. And I'll just start it again so I can show you, right? So the person comes in, they provide some information about their field. We pull soil conditions from Surgo and they can override those soil conditions. We pull weather conditions for that specific location from the weather API. The person then goes in and selects what their specific cover cropping goals are, and it subsets the full data set to provide only the cover crops that meet their goals, their soil conditions, their local weather conditions, etc. They can also enter in some information about what they're intending to plant so that we can do some visualization around planting windows. And there's a variety of different ways that people can then interact with this data. So, this was mostly designed based on what type of feedback we had from people who are actually going to use these tools. So we did a whole bunch of user studies at conferences, we held some online as well, that allowed for us to be able to really vet this interface before and this user experience before we actually built it. And so you'll see at the end of the day, somebody can then compare different cover crops and decide what's actually helping them meet their goals that's not necessarily already captured in it, and drill down. So they're walking away with maybe information sheets about one or two cover crops based on what they're looking for. So we'll be going into public beta. So this is a live site in winter 2020. So hopefully, if you are, or not hopefully, if you are interested in information about that, feel free to hit me up and I can send you a link once it's public. We're currently going through private beta. And so in each of the regions, we've invited cover croppers, advisors, people from each of those user groups to actually test out the tool and see if we need to do any final fixes before it goes into public release, which I'm very excited about. It feels like it was a year in the making, and it's exciting to get to this point. So from here, we'll be releasing the tool. I already mentioned that. And then I also talked a little bit already about some of the data next steps. Okay, so I think I'm coming to a close. So I just want to wrap up a little bit so we have some time for questions. So those are hopefully giving you a little bit of a glimpse of what's going on in my lab right now. At the end of the day, within my lab, we take this information ecological approach, and it involves these three core pieces, which is community-driven design, domain-specific modeling, and actual software engineering in service of resilient agriculture. I talk a lot about communities of practice. They're very important to me. These are three of the communities or four of the communities that I work with right now. So OATS here at Purdue is the Open Ag Tech and Systems Center, where I work with them on trying to explore the sort of the boundaries of open source ag tech. Open Team is another group, and there I've been doing a lot of human-centered design work and leadership with Open Team, as well as a lot of agricultural ontologies work. And then Precision Sustainable Ag is the group that I mentioned. I do a lot of the cover crops work with, and so I've been doing the decision support tools work primarily with the PSA collaborative. And if you're just generally interested in open ag tech, Some folks and I co-founded a grassroots community organization around open ag tech. And so if you go to gotech.org, there's a link in the bottom. You can come chat with us on the internet about what you think we should be building in the open source space. And I didn't talk about open source at all, which is rare because I love thinking and sharing ideas with people about why open source is important, but feel free to hit me up if you want to chat about that as well. And I think there's a link to my lab as well over there if you're interested. But let's put it all back together. In sum, I work with this range of communities to practice informatics. I do a lot of work in the design space, so you'll see qualitative research and human interaction falling into that first section. Within modeling, I shared with you some of the work in MOS, and not so much on the ontology development today, but that's sort of something that I'm happy to chat about in questions or in the future. And then under software engineering, a lot of our early work has been really focused around farm management, environmental assessment, decision support tools, and actually we've started now the microservices as well. So that's all I have to share with you for today. Thank you so much for your time and presence. I would also like to thank my funders and collaborators. And with that, I will open for questions.